All right, so I like to move around a lot, so it's great that I have this and I'm not stuck. Adrian, thank you, and Daniel and Allison, thank you for having me here. It's been a long time because I've interacted with a lot of you. I've known a lot of you for a long time, and it's absurd that I haven't been here. So it's been great, and it's been great to get inundated for 2 days and inundate back. Oh, that's loud. So I told you I had a loud voice. As Adrian said, this has been my baby, and this is really what I moved to the Jet Propulsion Laboratory to build. And we've long had this void in knowing the spatial distribution of snow-water equivalent and being able to constrain hydrologic models, constrain glaciological models, and understand ecosystem functions simply because we haven't known what that supply of water is. We started out from the very beginning with, let's see if I can do this right, with the California Department of Water Resources, Frank Gerke, who's the snow groundhog. You see him April 1st. He was out last year with Governor Brown in California, standing in a dry field. And we also worked with Bruce McGurk, who at the time we started was he was running the Hetch Hetchy operation for the city of San Francisco in the Tuolumne River Basin. And so from the very beginning, we brought in the stakeholders, the water managers, to make sure that we were able to get to them what it was that they needed. I mean, we knew that the science was going to benefit, but we wanted to make sure that the operational users were able to benefit from the very beginning. We've also worked with the USDA Agricultural Research Service, and in particular Danny Marks's group in Boise for some of the snow modeling, and then the National Snow and Ice Data Center. So what I'm going to cover today is the motivation, and I love being in a crowd like this because you guys know why we need this. I don't have to explain it quite like I do with the propeller heads at JPL. And then I'm going to give you a description of ASO's system and the computing, which is a really important part of this for the operational users, the product portfolio, just everything that we can bring out of the combined system, and then the mapping and modeling that we're doing in the western U.S. And in particular during the drought. We've been blamed for causing the drought because since we've been flying ASO, the drought has just been worsening. Thank God for this year. And then some of the forecasting with the ASO snow data and the ecosystem applications. We're flying more than just mountain snowpacks. And then where we're headed with an implementation for the operational program in the future. All right, so motivation. So about 75% of the precipitation in the western U.S. comes from snow. And it's been very interesting in the last couple of years to do the interviews and have people say, yeah, but I thought it was only 30%. DWR says it's only 30%. And it's because of the groundwater component. But you have to remind people that, therefore, those two mean that it's not sustainable. So we just have to figure out what's going to happen ultimately with the groundwater. The ecosystems are critically dependent on snowmelt and, of course, modulated by snow cover. And then, of course, groundwater and mountain block recharge. About 1.5 billion people worldwide depend on snowmelt or glacier melt for their fresh water supply, but mainly the snowmelt. The glacier melt is only really critical for base flow. And then within the NASA sphere, of the components of the water cycle, what remains to go into missions, either already existing missions or those that are in the chute to fly, snow water equivalent is not there yet. And so I'll talk a little bit about how this is a test bed. We do have snow albedo, but those combined are really critical together for understanding water resources and glaciology. All right, so I love coming here to Reno because it's to pay homage to also to Dr. James E. Church, who's the father of snow hydrology. Unfortunately, this is the federal snow sampler, and I didn't have his figure that I could find, or his Mount Rose sampler. The photos are horrible. So if you guys know where there's a great photo of them, or if I can take a picture of them, if they're on reserve here someplace, it would be great. But how many of you know the story of Dr. Church? Okay, not everybody. All right, so he was a humanities professor here at UNR, but he loved the mountains, and there were issues with respect to lake level in Lake Tahoe. So he took it upon himself and with a colleague went about building the Mount Rose sampler, which is now called the Federal Snow Sampler, to go up onto Mount Rose and start collecting snow water equivalent measurements to start correlating with lake levels and to understand that runoff. And his career really took off into that direction, and he became an international star, an international consultant in snow hydrology. And to this day, the Student Paper Award for the Western Snow Conference is the James E. Church Award. So at any rate, this is one of the great stars of UNR. And what's interesting is that to this day, we still use in operations the methods that he developed all that time ago. And in between, let's see if I can get this right. So in between, we introduced the snow pillow back in the 1980s. They started in the 70s and into the 80s. And these snow pillows are like water beds seated in the ground. How many of you have ever slept on a water bed? Yeah, see? How many of you know what a water bed is? All right, not everybody. So at any rate, these still have issues. Some snow pillows work really well. Some snow pillows don't work well. And you get bridging over them. Bears like to sleep on them or rip them up. And so various stakeholders really don't use snow pillows in their forecasts, and they continue to rely on the Federal Sampler or the Mount Rose Sampler. All right? Now, look at the spatial extent that's being covered here. This is Frank Gerke, the snow groundhog, along a snow course. It's about a football field's length, and you make 10, 12 measurements along that length, average those, and that gives you your indicator metric for that area. And you use that with 30 years of record then and weave that into your empirical model to try to understand what kind of runoff you're likely to get. All right. Now, this is another example of this. So Popular Mechanics was really excited about the federal samplers in the 1940s and didn't do any articles on it until 2014 when they did the snow plane. So it shows two things, right? We've advanced, and also you can tell that they use really lousy paper in the magazine because you could see through even with the PDF scan. All right, so we also think that we have it pretty well mapped around the western US, and arguably we have the best measurements around the globe. In Switzerland, there are 400 snow depth measurements, but there are only 40 snow water equivalent measurements, probably because the terrain is so steep and you can't put a snow pillow on steep terrain. But we do have it pretty well nailed across all the mountain regions. However, when we zoom in, that's when we begin to realize that we need to have a better measurement. Now, I'm not sure if you can see this, and my colleague back there refused to dim the lights up here. Are you guys able to see the screen? All right, well, I'm going to point out, so the little dots here this is the Tuolumne River Basin, all right, and Mount Lyell is down here. The Hetch Hetchy is down here, and there's a pillow here, and then snow courses in here. There's another pillow here on the E, that's the Slide Canyon, and then a couple here in Tuolumne Meadows, and then one up at, oh, nice. Oh, it's great. Is that better? Great, thank you. And then another at Tioga Pass. All right, so we have, 8 measurements, some of them daily measurements, some of them monthly measurements in the whole Tuolumne River Basin. 1,200 square kilometers, 460 square miles, and an enormous gap in here. No measurements whatsoever. And this is also the big head wall that faces off to the southwest that collects an enormous amount of snowfall. because of the orographics there. So we really have no idea what's going on in here. And at the snow pillows, this snow pillow stayed on 32 inches all of last year, which was wrong from the very beginning and all the way through the year. And then we had problems with a couple of the snow pillows down here. So we were really, really sparse on information. And if you look across all of the snow pillows in the western US, they really are pretty sketchy measurements, right? So this is the way that we see snow water equivalent now, though, in the Tuolumne River Basin. But what we want is 39 million times more coverage. Right, this is the way that we want to see it. We want to see it wall to wall, and we want to be able to add up all of the volume of snow water equivalent in the basin and in sub-basins, and we want to be able to understand the distribution of melt associated with the topography and synoptics and on and on. All right. So that's the snow water equivalent piece. Now I'm going to go over to the other instrument in the plane. All right, I'm doing the LiDAR first, and now I'm going to do the spectrometer. So what drives snow and ice melt? You hear a lot about temperature. We use degree day models, so you turn the temperature up and things melt faster, right? Well, it turns out that in these, for instance, in these 5 days from the Senator Beck Basin, the highs were 13 to 15 degrees C. Hot days at 12,000 feet. The net flux here is the energy that's available for melt, is the black trace during these days. And then the red trace is the net solar radiation. Right? So about 90 to 95% of the energy that goes to melting snow comes from absorbed sunlight. So it has modulation by the cloud cover and, of course, topography, but also the modulation by the albedo. And that's the big uncertainty and the big variable year to year. All right? And this runs from Greenland, the Swiss Alps, Rocky Mountains, all the way down to Antarctica. It doesn't really matter what latitude you're in. And this is kind of why glaciers form in deep cirques that have no snow. Have no sun. All right? Okay, now this is a piece that I'm going to show of my work. And this is the only piece that I'm going to show about dust and snow melt in the Colorado River Basin. But this is another thing that we focus on, and I work on with several of you. This is just above Telluride, and Silverton, Colorado's back over here off this ridge. So this is a paper that we have in review right now. We wanted to look at what controls the steepness of the rising limb of the hydrograph in several rivers coming off of the San Juan Mountains, surrounding where we have energy balance towers and radiation towers. And so what we've done is just taken the slope here from the onset of the rising limb to the peak. And it turns out that the average of all of those slopes is the same as the slope of this line. And if you look at, I grew up in Colorado, and I expected that in springtime, if you got a warm spring, you're going to have a heavy runoff. It's going to be a really fast rising limb, right? I'm still having troubles with the results, even though I know they're there. But what we found was that these are well ordered. So the steeper the rising limb is consistent with greater dust, greater deforcing, greater absorption of sunlight in the snowpack. Right? So that modulation of the snow albedo is really how fast that snowmelt runoff comes out of the basin. And it turns out it has no relationship whatsoever with temperature. A bit crazy. My co-authors, we still say it's there, it's true, but how's that possible? So all of that was to set up why it is that we have the instrumentation that we do on the plane. And so to know the magnitude and the timing of snowmelt runoff requires that we know how much mass there is, just how much snow there is that can be water, that can come out, and then what's the snow albedo? What's that modulation of the melt timing? All right, so here's the plane at the Mammoth Airport. We fly out of the Mammoth Airport most of the time. It's a King Air. We do have a little GoPro mount up here We're going to get one under the tail as well, which gives really fantastic imagery, but great perspective on what we're seeing out across the plain. And then there's a nadir port right here under the N41J. Don't write that number down because we're getting a newer plane with greater fuel capacity. So I'll give you those when I'll give you the tail number when we get the new plane, which would be Monday. It's coming. And then you can run it into FlightAware and you can watch us flying the mountain basins. So the two instruments are a scanning LiDAR, sitting here. This is a Regal Q1560. It's a dual laser scanning system, so slightly forward, slightly backwards, so you get a great 3D view. You can get the fronts of buildings, you can get the backs of buildings, backs of trees, backs of cliffs. It's a 1064 nanometer laser, so we only have about a centimeter of penetration into the snowpack, so there's no real ambiguity as to where the snow surface is. And likewise, you get great penetration through the forest canopy, so you can get a nice hard return from the snow surface underneath the forest canopy. And then we do full waveform with this as well, so if you want to look at vegetation structure, you can have that full characterization at very high resolution. And then a 60-degree field of view. The spectrometer is a CASI 1500. Both of these are off-the-shelf instruments. And it's a 72-band spectrometer across the main part of the solar spectrum. It's a visible near-infrared silicone detector, which is why it cuts off at 1.05. But the goods in terms of snow albedo variation happen in the near IR due to changes in snow grain size, and then in the visible wavelengths due to impurities, the dust, the black carbon. Right? So those are the two components that we weave together to treat the mountain snowpack. We fly in a non-pressurized aircraft, and this is an engineer and a recent PhD geographer. So those students and postdocs, this is the kind of job that you can have. It's a hell of a lot of fun. They're both smiling under there. And this is how we go about covering entire basins. So this is the Merced Basin above El Portal. All right, so from the high elevation snowpack all the way down through Yosemite Valley in here and then down toward El Portal. And we just mow the basin back and forth. And an important piece of the operations here was figuring out how to get the pilots to turn faster. We have, what do we have here? It's about 20 lines, 20 flight lines. And initially we had 3-minute turns out of them. So we had nice moseying turns. Nobody was throwing up in the plane. Everybody felt comfortable. But it's 3 minutes every turn. And we began to realize that we started asking, can you turn it a little faster? And it became a competition between the pilots. So we got it down to 58 seconds. So we were carving over 2 minutes off of every turn, and so that bought us, in this case, 40 minutes of time online. Right? So that allows this to start to open up further to an operational program. We can cover more terrain. All right, and this is the way the program has developed. We started in 2013. Well, we started in 2012. We did our first snow-free acquisitions in the summer of 2012, and then started flying the snowpack in 2013. And we have snow hydrology measurements, ecosystem, desert disturbance, fire scar measurements, and then the program is in development, in various forms of development, and I'll talk about that in a bit. We started out in the Sierra and in the Colorado Rockies, and this has just grown as our LiDAR capability has increased and our flight altitude has increased, so we've really been able to expand this program. We fly in the Uncompahgre Basin, which is in the Colorado River Basin, and then also over in the Rio Grande, in the Conejos and the Upper Rio Grande, in a project for the Colorado Water Conservation Board and NCAR. And then this year we'll be adding the McKenzie River in Oregon. We're doing, I'll show you this in a minute, but we're doing GPM validation in the Olympic Peninsula, and then adding the ARS, the USDA ARS Reynolds Creek Experimental Watershed in Idaho. And this has really been an interest of the NASA program manager, Jared Enton, who's the terrestrial hydrology program manager, to expand this program so that we can entrain more and more users. And if we just do a couple of basins, people are working in their own basins, and they want to see it come to a theater near them. Then we've been flying in the Colorado Plateau, Grand Canyon, and trying to remember. I think this is in the Lake Mead area. We've looked at the at Tamarisk in the Virgin River, and then up the Owens Valley, and then the fire scars from the King Fire and the Rim Fire. And that's been in collaboration with Dave Schimmel, who I recommend you have come up here. And then we have a project that we're starting soon with the Forest Service in the McCollum Basin to look at the power fires' impacts on snowmelt runoff. And that's important for the Forest Service, the East Bay Municipal Utilities District, and then Pacific Gas and Electric. And then gradually this program, what we're working on with the state of California is to expand it to the entire Sierra Nevada in a weekly flights. And then I'm also going up to Oregon here in about 2 months to talk with them, the Department of Water Resources and the Deschutes River Conservancy, to talk about ASO Oregon. And then in the Colorado River Basin and Wyoming and Idaho, they're interested in getting this rolling. And then expanding even further in the Rio Grande with Colorado, New Mexico, and Texas. So it's crazy. The phone is ringing all the time, and it's tough to stay on top of this. But fortunately, we have a great team to make this happen. All right, so what are the ASO products? The main one that everybody wants to talk about is the snow water equivalent, because we've been looking for this for a long time. I came out of Jeff Dozier's group, and we tried with radar. But the problem with radar is that just for the very reason that your microwave works, is that it absorbs, the water in your food, the water in your tea, absorbs that radiation. Well, same thing happens with the snowpack, and that's the time of year when you most want to assimilate snow water equivalent information. All right, so radar loses that signal. It has issues with vegetation, so the vegetation essentially blocks the signal, even if it was dry snow underneath that, and there's a lot of snowpack that is underneath the vegetation. Right? So that's why we came to the idea of going to it through the snow depth measurements from the LiDAR. And in particular, this is okay across the landscape because the variation in snow water equivalent comes primarily from the variation in snow depth. Snow density itself bulk snow density doesn't vary much across the landscape, and it does so in ways that are predictable. Right? Snow depth, it's a little more difficult to predict across the landscape. Right? And then going through time, the densification process is fairly predictable as well. So this is how the procedure works. So snow water equivalent is the depth times the density. Right? That gives us kilograms per square meter. And we measure with ASO the snow depth. So we fly when there's no snow on the ground, and then we fly afterwards. The difference between those topographies gives us the snow depth field. The snow density we measure with Danny Marks's ice snowball model out of the ARS. And we've found over years of modeling that they model the density quite well. It's only when it gets really shallow that they start to lose control of the partitioning of depth and density. And then ultimately, this grid cell wise multiplication gives us the snow water equivalent, which we produce in this particular case at a 50-meter resolution. All right, so do we want to get rid of Frank? And do we want to get rid of the program? Absolutely not. The ground measurements are critical to constraining the modeling. We use that information to nudge the modeling, because the modeling is not, it's absolutely not perfect. And we're also looking at some other microwave technologies that may be able to give us snow density sampling across basins. So stay tuned on that as well. But this is the piece of the puzzle that is the most uncertain, even though it's not terribly uncertain. But the density is the one that if you want to go out and dig snow pits and measure snow density for us, please raise your hand, come find me after the talk. There will be lots available to do that. All right, so the scanning LiDAR products are the snow depth, a digital surface model, and a digital terrain model, right? So the shrink wrapping of the surface and then cutting down all the trees. And the latter is the important for the hydrologic function. And then terrain metrics, of course, slope and aspect from the topography, and then the vegetation structure from the waveform, or just the simple discretized LAYS files where you just have a few returns as shown right here. So we provide either one of these returns. And then the nice thing is this hard ground return where the snow surface is. And then vegetation height. Well, I was going to make an aside, but I'll do it after the spectrometer. So we also provide natural color imagery, just an RGB composite, and a surface classification, broadband albedo, and we do broadband albedo for entire composites or also for the snow component of each grid cell. The grain size for each grid cell, we get that from the spectrometer out in the longer wavelengths, and then the radiative forcing by impurities, the dust and the black carbon in that basin. All right, so between these two sets, all right, we can very quickly set up a hydrologic model. Right? There's an enormous effort that goes into constraining a model, establishing a model for a basin. You've got to go out and figure out where your vegetation is, prescribe that, what are the vegetation heights, where are the grasses, where are the shrubs, and then what's the hydroflow in that basin. And you've usually been relying on fairly coarse digital elevation models for that flow routing. Now we have very high resolution information on the topography, on the vegetation, on the classification, on the bare rock, the talus, on and on. So it is a game changer in terms of providing that information to establish those models. A couple of pieces that are missing: soil moisture, soil depth, soil properties, right? And so we're looking at ground penetrating radar on a helicopter to at least try to sample the basins to establish those fields. But there's not yet really a great way to set that up. All right, so in working with the water managers, and in particular working with the California Department of Water Resources, they are establishing PRMS model. It's the USGS Precipitation Runoff Modeling System they say they're going to do it in all of the basins in the Sierra Nevada, but it's been coming fairly slowly. And so with Bruce McGurk, who ran the Hetch Hetchy operation, he had already started to set up a PRMS model for the Tuolumne, which wasn't done yet from DWR. But we started working with him from the very beginning, and working with his hydrologic response units, we were able to put together an automated processing to have those ready for him to constrain the model. We also are doing just the ASCII reports that the water managers like to have as well, just to be able to keep track of how the total snowpack water is changing, what the mean snow water equivalent is, on and on. And then we also have these discretized according to elevation bands. And these are automated reports that come out and then are shipped out to DWR and the various water managers. All right, so I told you I was going to talk about the compute system. Get a little water. Let me do my Marco Rubio. All right, so I forgot to mention that the reason that I decided to go about doing the Airborne Snow Observatory was I was sitting in a talk in 2008 by Greg Asner, who's at Carnegie Department of Global Ecology over at Stanford. And he was presenting his work with fusing imaging spectrometer and scanning LIDAR to look at tropical biodiversity. And I was totally zoning out on the tropical biodiversity stuff. And just thought, oh, we can do snow water equivalent and we can do snow albedo. So I always want to make sure that, that he is honored as well for having put this together and really suffering through, through this when the technology was not so great. The other reason I bring this up is that we have a couple of members of our team who were involved with Greg's activities over the last few years. Among those, Joe Boardman in Boulder, Colorado. And what I told the team at the very beginning was, we're going to turn the products around in 24 hours so that we're relevant to water managers. And they said, oh, okay, yeah, how much are we pulling off the plane? About a terabyte. And there are 2 processing chains. And then Joe took me aside, and Joe had been doing the processing for Greg. And he just said, look, I didn't want to say this in front of everybody, but there's no way, man. Absolutely no way. It's going to be a couple of weeks. Greg takes a couple of months. It's going to be a couple of weeks. There's no way we can do 24 hours. And I thought about it and then said, no, we'll do it in 24 hours. And it turned out we had a great team, a great compute team, and we started thinking about in various ways. And we're now down to about 20 hours turnaround for the Tuolumne Basin. All right, that includes the modeling, the distributed modeling, the full integration of the products, the distillation all the way out to ASCII, and full integration across the basin, et cetera. And that was really a testament to the compute team that I have and the amount of caffeine that they drink. So we have 2 processing chains, and they're interwoven. And I think I need to show we've added some of the connectivity among these to really make the products more robust. So I need to add some arrows back and forth between these. But this is coming through the base stations. We've thrown out the base stations. We're now using RTX on the plane, so we have the real-time updates on the position of the aircraft, as well as the IMU, the inertial measurement unit, which itself is what really allows this whole thing to work. Without that, if we don't know where we are in the plane and we don't know which way we're pointing, you'll put pixels down in all of the wrong places, and you might as well just be doing federal samplers. So this comes down through this chain to get to the surface height. We get the snow depth exposed, snow depth beneath the trees. We fuse those back together. We bring in the snow, that core water equivalent. Likewise, on this side, we bring the raw flight data and into the calibrated spectral radiance. Then we go to the spectral hemispherical directional reflectance factor, and then to spectral albedo. And we have the side products of grain size and dust and black carbon radiative forcing, but the snow albedo. And again, these are the components that we ship off mainly to those water managers in the 50 meters. So that is constraint on the topography. Yeah, exactly. So we update the topography because the snow surface is changing all the time. So we use the latest surface topography to then do the topographically corrected reflectance retrieval. Yeah. And then we also use the spectrometer to come back onto areas where there's some uncertainty in the measurement. So in rough terrain and slight geographic geolocation issues, you can think that you have snow depth there, but it's just the geolocation issue. So we use the spectrometer to cut out. All right, so these are some of the, this is my favorite shot. This is from Mount Lyell, and back in 2013. The surface of the ice now underneath this is about 8 meters lower than it was at this time. Going really fast. So this is the Lyell Glacier and the McClure Glacier. And if you look closely, you can see this tinge of dust deposited here. And this has been one of the surprises for us flying in the Sierra Nevada. Can you see it, Joe? What's that? Oh, yeah, it's probably black carbon. It's kind of yellowish black carbon, right? And you can see it over here as well. But this is a color composite from the spectrometer on top of the topography from the scanning LiDAR. We turn that into the broadband albedo, and you can see where Joe's yellow black carbon has dropped the albedo down here to about 0.5, and then up high on the glaciers, it's still up around 80% albedo. Right? So these areas are going to have really accelerated snowmelt once we get the sun up over the horizon. I guess May 12th we are already. And then the big daddy here, the snow depth field, this is the one that we spend a lot of time staring at because we have thought for so long about what the distribution of snow water equivalent is and what snow depth is, and we've really not known what it is. We've done this extrapolation, we've done lapse rates, we've interpolated between snow pillows, but finally we have an idea of this kaleidoscope of snow depth distribution. It's really, really wild. So if you guys want to look at high resolution snow depths, come look at them. They're gorgeous. They're lots of fun. And they won't make you sleep, I promise. All right, now this is where I need to the mouse. So what I'm going to show you here is it's going to be a time series of these. We're going to start in 2013 and we're going to run all the way to 2015. So each of those springs. And then in the corner here will be the time series of basin integral total snow water equivalent. All right? So how much water is in that total snowpack? Hopefully it works. And you can see the cursor go sliding across here. All right. Here we go. And this first shot, that's the most that we've ever measured. It's all been lower than that. So this, again, this is the Tuolumne Basin. Following the total snow water equivalent, we started out up here around 300,000 acre feet. And then in 2014, we start out below 200,000 acre feet. And there's a really strange convergence that happens here in June toward about the same amount of snow water equivalent. We just think this is a pure coincidence. And then with the Turlock Irrigation District and the Modesto Irrigation District funding from them, we started flying earlier this last year into the winter. So we had a mid-February flight and an early March flight. This was the date of the proclamation of the worst snowpack in 500 years. And then right after that, it snowed a lot. And then during this period, it rained like crazy. So 2015 didn't end up being as horrible a year as April 1 snowpack was suggesting it was going to be. It was definitely not a great year, but it was not quite as bad as we would have thought it was going to be at that time. All right, so I just want to take you through the photo gallery, the image gallery here. This is Rush Creek. This flows off into Mono Lake. And we provide these data to Southern California Edison, the forecaster in this basin. And he's using those for his forecasts. This year it allowed him to not make a factor of 2 error in his forecast. And it saved, I think it was a couple $100,000 just with those particular measurements. Then here's the Rush Creek time series. And this will be SWE and albedo, that basin. And so there are 3 parties that have interest in these data. There's Southern California Edison, who runs it through their system. There's LADWP, who owns that water now. And then there's the Mono Lake Committee, which keeps an eye on LADWP to make sure that they're not taking too much water and they're making sure that the lake reaches its appropriate level. So it's been really interesting to bring the 3 of them together into one room and see who's most tense. They're all pretty cool. All right, so this is to give you an overview of the sampling program right now, the ASO program in the Sierra Nevada, and we're looking to the evil Southern California, where the water all goes, so we fly the Kings Basin, which is a agriculturally really important basin, and we work with Steve Haugen, who's the water master for the Kings. He's really interested in the data from the standpoint of meeting his allocations. He's got a lot of important ag users, and he gets enormous heartburn in the spring and not very much sleep because of his lack of knowledge of the snowpack. And what he told us this year was that he can finally sleep because he knows how much snowpack there is, and he's not going to make big errors that affect farmers' lives and family farms. We fly the Lakes Basin here right by Mammoth, and the airport's down over here, so it's easy for us to fly this. Again, here's Rush Creek. We've added Lee Vining Canyon here. Here's the Tuolumne, and we're extending the program out over here and the Merced. And then a week from today, I'm having a conversation with the Bureau of Reclamation to fill in the San Joaquin, put together the funding for that so that we can get this this mid-section down toward the Kern. We haven't talked to them yet, but at some point in the next few years, we're probably going to be at an entire Sierra Nevada program. The cooperators really want it, and I think it'll be really interesting to talk to people up here in Reno as well, on the water management side. All right, and then I mentioned the Conejos. That was that project with the Colorado Water Conservation Board, and the Uncompahgre watershed flowing into the Colorado River Basin. All right, so how accurate are these results? Well, so what the manufacturers say for the LiDAR is that there's about a 10 centimeter uncertainty in the range measurement. We find with our snow depth measurements that we get about 8 centimeter uncertainty. And we have some constraints that we use using bare ground to lock in the surfaces, so that helps. That's at a 1.5 meter resolution. But remember, we coarsen to 50 meters. That's where we assimilate the snow density information. And so when you coarsen that and you have no bias in the snow depth estimate, then that plummets to less than a centimeter uncertainty across that 50 meter resolution. And then the density uncertainty, our best understanding of what we have right now through what's an elevation adjustment is that we get about a 17 to 20 kilogram per cubic meter uncertainty. That's pretty tight, and we're not terribly comfortable with that number yet. We feel like it's smaller than what the actual number may be. And again, that's why I'm calling out wanting to have as many density measurements as we can get out there. So any volunteers that we have, and NASA will pay for your time in the field. So all graduate advisors, please free them up to come work with us. But so this multiplication then of the uncertainties carries us into a scenario where we have about a nominal 5% uncertainty. It depends on the scenario, but for the most part, it's really tight on a grid cell by grid cell basis. And then when you integrate that to the whole basin, it's we're quite confident in those numbers. All right, I need to hurry this along. I just want to point this out. So these are the 10 stations. This is the aggregate of 10 stations that the Hetch Hetchy team uses for their forecasting and have for decades. Looking at the percent of the median April 1. And this is in 2014, was not a great year. And then over here, these bars are the total basin snow water equivalent from ASO. And the main point I want to make here is that when the pillows and the snow courses die out, they've gone blind. But at that point, there was still about 80% of the snowpack that remained in the basin. Right? This is their slide, actually, and they show this in every talk that they give right now to explain why they want to put money into this program. Just from that standpoint, it's terribly important for them. All right. And this is what Wes Moynier, the head of the Turlock Irrigation District, called my $1 billion scatter plot. So the next thing that they wanted to look at was how diagnostic was the ASO snow water equivalent during a particular acquisition of how much runoff there was going to be. So the AJRO, April through July runoff. In this particular case, they only ran to July 1st because everything ran dry by July 1st. It wasn't really worth it to run it out an additional month. And when Chris Graham put this together, he took a week before he sent it to us because he was sure that he had plotted an ASO product versus an ASO product because the R-square is 0.983 There's no way that with independent data sources that you can get that. But he went back over and over and concluded he had actually done it right. So what this tells us is that, and tells them, and why they use this information now, is that on April 7th, say, here at this point, right, if ASO is telling them they have 210,000 acre-feet of water in the snowpack, right, so we've missed the previous week's melt, so we haven't been able to capture that water that is already engaged and ready to go into the system, not to mention the rest of the basin where there has been rain, et cetera, right? But if it's telling them that they have 210,000 acre-feet, then with great confidence, it's telling them they're going to get 310,000 acre-feet out through the rest of the year. So if they have a 100,000 acre-foot deficit in the reservoir, they can know confidently. They don't have to hedge anymore. They don't have to worry, even though their number one metric is they have to fill the reservoir. Because back in the early 90s, it dropped with some sketchy management. It dropped, plus drought, it dropped down to about 4 feet from the bottom of the intake. And this is the water supply for the city of San Francisco. So San Francisco could have been cut off from water. So now their number one metric is thou shalt fill the reservoir. And because of that, they can't optimize with respect to meeting their environmental metrics. They can't optimize with respect to hydroelectric generation until they've filled the reservoir. Right? But this allows them to know, all right, I'm going to lop off that 100,000 acre-feet that I know I'm going to get, and then I can get aggressive with generating electricity with the remaining 200,000 acre-feet, and I can meet my environmental metrics down the Tuolumne River in a timely fashion when the temperatures are right, on and on and on. All right, PRMS implementation, this is the way those look, those products that we generate. We also are doing, with Bruce McGurk, doing the assimilation of the ASO data and into a forecasting mode. We're also doing this with Danny Marks with his iSnowball model. What it's showing us is that if you don't include the distribution of snow water equivalent, in this particular case, you would have thought that you had more water than you actually did. Whereas when the model starts receiving the proper amount of snow water equivalent, it realizes, oh God, I got to back this off, and drops that into more accord with the inflow observations. And this has been an interesting process, trying to get the PRMS model to use the truth, or this very close approximation to the truth. For so long, we've been stuck with such poor information. So it's interesting watching the modelers deal with this thing that they've been asking for all along. They're excited, and then they suffer, and then they're excited again. All right, I'll blast past that. But I want to show that Brian Henn, who's one of Jessica Lundquist's students up at the University of Washington, is using the ASO data in concert with streamflow to accurately get towards precipitation distributions. And he's working on this with Martin Clark. And then we're also evaluating the SNODAS product from NOAA, and that has been the main source of distributed snow water equivalent. But those guys understand that they're throwing all the products in there, and there's lots of interpolation and extrapolation. This is the distribution from ASO, and it's kind of hard to see with the lights here, but it's way off. We've also looked at it in the Tuolumne. In 2014, it was consistently off by a factor of 2. So 100% errors. So we're starting to know what it is that we have not known and how badly we have known it. All right, so this is the program I showed you again. We've added, so this is from the Kings down here, the Lakes Basin, Rush Creek, Lee Vining, the Tuolumne, Merced. We've extended the Tuolumne to include the Cherry and Eleanor reservoirs, so we'll be flying that this year, and the McCollum Basin in that project with the Forest Service. All right, so what about Lake Tahoe? Shay was asking me yesterday. He was being very gracious about it, and then finally got demanding. And I told him, look, where's Mike Dettinger? Is Mike Dettinger here? I'll have to give him hell. At any rate, we need to figure out who the stakeholders are and start talking to them about putting together the funds for this to fly the rim of Lake Tahoe. I think it'll be really important. These are all the growing partnerships, and Idaho Power is on this list now. So it's getting too numerous to keep track of. But eventually we want to get to the whole of the Sierra Nevada, the whole upper Colorado River Basin, over into Idaho. In the Great Basin, there's interest in Utah, and even in Arizona, down in these ranges. All right, beyond the snowpack. So back in 2013, we acquired data along the Virgin River and the Muddy River to look at the tamarisk distributions there. And then for Dave Schimmel, we flew the Kingfire Scar, and this is just some of the LiDAR data from pre-fire, post-fire. It's fantastic, fantastic data. Boy, it's hidden back here, but there's Great Basin agriculture back here. So when we transit between Colorado and California, we're able to pick up these areas. These are agricultural fields back here. And then we made an attempt at getting the EPSCoR transect over in the Snake Mountains, and unfortunately it was cloud covered during that time. So we're going to try again this coming spring to hopefully pick those up. And then, of course, we have, with our snow-free acquisitions, then we get a great shot at what remains of the Sierra glaciers. And we're working with Greg Stock, who's the park geologist for Yosemite, on the Lyell, the McClure, and the Conness glaciers. And then I think I mentioned we're doing validation of the global precipitation mission with ASO. We'll be flying up on the Olympic Peninsula right here, and hoping for some lack of cloud cover sometime soon. But man, look at Mount Olympus here, and oh, it's gorgeous. All right, so I think this is my last slide. So ASO really has been about pathfinding, and the reason I went there was to be able to build this and provide this to my communities. My communities being hydrologists, snow hydrologists, glaciologists, ecosystem scientists, carbon scientists. And because I realized we had a great opportunity, but nobody was really doing it for that community. And so where this has led is the straight ahead research science, of course, with the water cycle. But anymore, when you do water cycle science, it's inescapable that you're dropping into applied science immediately. Right? They're always looking over, and we're always looking over. And it seems in the last few years that we've really seen that wall between the two drop. That research to implementation to operations is a real possibility. So this now, looking at forecasting, looking at land use, land cover, and agriculture is a great opportunity for us. And then we've gotten very quickly, because we started with DWR and we started with Hetch Hetchy, we were very quickly able to get towards water management. And the cooperators have expressed to us that they, by God, want this to go ahead as part of their infrastructure. They see this as the next maturing step of where they need to go to be able to do their jobs for their constituents. Likewise with the land management and forest management. And finally, this is providing the basis and the test bed, at least one of the test beds for the next NASA snow mission, or I should say the first NASA snow mission, because we've not had one. And there have been a couple of tries. There was the SCLP in the last decadal survey. It failed because there wasn't a reliable microwave measurement or algorithm. The Europeans tried another version. Likewise, the same result. There was no reliable retrieval. Now we have a reliable retrieval. We're doing it on a weekly basis. We're doing it all over the West. We have the Chileans who are interested in us bringing it down there. The Swiss want us to bring it there, and even the Nepalese. But we, of course, can't cover the globe with airplanes. It's cost prohibitive. and there are lots of places where our planes would get shot down. So we're not that interested in doing that. So, at any rate, this is the last slide, and this is just to show you the website and the URL. This is aso.jpl.nasa.gov. The products are available, and if you see something that you know we have that we don't have up on the website, please let us know. We're happy to send out disk drives. Some people actually get into them. The products are also going to be delivered by the National Snow and Ice Data Center here soon. We're working through the archiving and distribution. But I really want to encourage the grad students in particular. This is a great time, not just because of ASO, but all of the missions that we have up right now, SMAP, and those that are coming, SWAT, GRACE follow-on. The water cycle is going to get great observations over the next coming decades, and this being the century of water, you guys are really in the right program at the right time. So I'll stop there.